The relational database model, or specifically a relational database. What is it? In its simplest form, a relational database is a set of tables. As you can see from the diagram, we have a number of related tables, such as act, show, venue, for a concerts set of tables. A table defines the structure of an object. In the diagram, we see the structure of the venue table or object declared horizontally, with 1, 2, 3, 4, 5 fields. Those fields being venue ID, name, city, state, and country. Many objects can be stored in each table as rows or tuples. We can see that the columns or fields declared as venue ID, name, city, state, and country are duplicated, as shown by the 10 rows displayed on the screen. These are 10 venues in the Northern California area. So we've seen that the table is two-dimensional in structure. The structure of each row is declared horizontally, and the data rows are inserted into that structure and duplicated vertically. In the relational database model, tables are related to each other by parent-child relationships. As you can see in the diagram, the venue and show tables are related, describing many shows for each venue. This is denoted by what is called the crow's foot. This relationship is actually one and only one to 1, 0, or many, which means there can be many shows for a venue, or there can be no shows for a venue, or there can be one show for a venue. Thus you could have a venue without any shows. How the relationships, or the parent-child relationships, function is that a child table will contain the repetitions contained within the parent object. To describe this in detail, we go into normalization, which we will reach at a later stage. The point to make at this point is that the link is maintained by storing the venue ID in the show or child table, as we can see by venue ID foreign key. What this means is that all shows for a specific venue can be accessed later on by retrieving data from both the tables at once. What does a relational database accomplish? It organizes or allows organization of data and information. It increases the performance or the speed of the database or data access because you can access parts of that information rather than accessing everything all at once. It's easier to search. It allows you to search within specific objects, such as venues or shows, rather than shows within venues all at the same time. It saves space. Duplication or duplicated information is removed into separate objects. Now let's go through some technical jargon. An entity. What is an entity? An entity is the same thing as a table. In the relational database model, a table is known as an entity. The objects on the left are all entities. What is a relationship? A relationship is a link or relationship between those entities. For instance, you can see the relationship between the venue and the show, where the venue ID is stored in the show object or entity. There are many other relationships on this diagram. One that's particularly interesting is the self-join relationship on the category object, where a category can have a parent category. We'll get into that further at a later stage. Attributes. This diagram shows the attributes once again in the show table. Show ID, category ID, act ID, venue ID, and show date. A data type. A data type is the map or description of the type of data that's stored into an attribute. A data type can be a character data type, a data type, a number data type, many different types. Now we're going to go through some example schemas. The three schemas I'm going to show you are, the first is for a game, the second is for concerts, and the third is for employees. The game schema. A player playing the game can play with many characters. Each of those characters can have an individual skill, which he's particularly good at. Each character can belong to a single guild, or a guild can have many characters within each of the guilds. Since a player can have many characters, the result is that there's actually a many-to-many relationship between the player and the guild. This many-to-many relationship is related by the character guild. The concert schema. In the concert schema, we have venues, acts, in other words, the names of the bands or the performers, and then every show that the act performs at each venue. Thus, between venue and act, there's a many-to-many relationship. Also, there's a supporting act for each act at each show. Thus, the many-to-many relationship between act and show resolved by supporting act. We also have categories of shows, such as jazz festival, rock concert, ice show, etc. We also have a rather interesting self-join here, where a category can be part of a parent category, as in rock shows could be divided into grunge rock or heavy rock, etc. Also, we have the ticket object, where there can be many tickets for each show, and we have a price object, which is declared separately because we could have specific pricing levels for each venue, but they could be altered by each individual show, since a boxing match will occupy the middle of the whole center of the stadium, as with an ice skating show, but with a rock concert people would be sitting down there. The employee schema is probably the most complex, since it has the largest number of entities. In this schema, we have an employee who works for a particular company in a particular department within a particular division. Each employee works on projects based on the route through assignment and task. A project can be of a specific type, and a project can be involved with a specific product. Normalization. What is normalization? Normalization consists of a number of steps. Normalization is synonymous with relational database modeling. In other words, normalization is relational database modeling. Normalization is, in general, a process of elimination of duplication from a set of data into specifically identifiable objects. There are 5 normal forms: first normal form, second normal form, third normal form, and fourth and fifth normal forms. It is recommended that only first and second normal forms are used extensively, and third normal form is used sparingly only when it's necessary. Fourth and fifth normal forms are generally for academics, and in commercial environments they cause more performance problems than not using them. So what is normalization in terms of normal forms? What is first normal form? First normal form attempts to remove the repetition within datasets by creating one-to-many relationships. Second normal form separates dynamic from static data by creating many-to-one relationships. Third normal form resolves many-to-many relationships into unique values. Fourth and fifth normal form go layers further down the net. I don't want to simply dictate what I have on my slides here. I would like to get into a more useful explanation. The descriptions for describing each normal form level, first to fifth, I find extremely complicated. In reality, I find that most developers and database administrators don't really understand what those steps mean, and most normalization is done instinctively by experience. So I'm going to try to demonstrate exactly how these levels of normalization work within the scope of what I think is applicable. First normal form. Looking at the diagram, you can see that the purchase order table on the left has not been normalized because it contains customer details, it contains each purchase order plus the items on each purchase order. In other words, when you go to, say, Amazon and you buy 5 books, the table on the left would have your address and phone number, plus the date that you ordered, when it was shipped, and the total amount, plus all the details of each book. The first normal form removes the details of each book into 2 separate objects. Basically, what you would end up with is the purchase order and the purchase order item. So on the purchase order, you would have the customer address and phone number and details, you, since you ordered the books. In the purchase order item table, you'd have the description of each book. What this effectively does is separates the duplicated information from the purchase order table into 2 separate tables. That is what I call first normal form. We're creating one-to-many relationships. The one-to-many is described by the horizontal line across here, denoting one and only one, and then the many side of the relationship is denoted by the crow's foot, implying that every purchase order, in order for each purchase order to exist, it must have at least one purchase order item, and there can be many purchase order items. In other words, if you place a purchase order with an online book company, you have to order at least 1 book, but you can order more than 1. Second normal form. I like to simplify second normal form in the following manner. On the left we have the first normal form from the previous diagram, and on the right we have the same entity structure with second normal form applied to it. Second normal form, in my eyes, removes static information from the purchase order table. I'm the customer. My information is static. If I go on to an online bookstore and I order books 20 times in a year, my name and address are static. They're stored. Each purchase order is not static. There's no reason why I need to store my customer name and address every time in each purchase order. It's a total waste of space. So I take my address and my phone number and my general details and I push them out into a separate entity. And I end up with a 1-to-0 one-or-many relationship to the purchase order table. This implies that I can have my details stored at Amazon. Not that I would want my credit card stored there, but I don't have to actually order any books. That is second normal form. First normal form creates one-to-many relationships, and second normal form actually creates many-to-one relationships. Third normal form. You'll notice that this diagram is somewhat greener, as in the first and second normal form diagrams were blue. These are green. The reason why I do this is because anything below second normal form I don't recommend. Third and fourth and fifth normal forms go into far too much detail, and as I already said before, they cause far more problems with performance than were you not to use them. Third, fourth and fifth normal form cause far more problems with performance than the descriptive detail levels problems that they actually resolve. I would recommend not using third, fourth and fifth normal form. The only circumstances where third normal form is utilized is where it's actually needed by the application. In modern day applications, typically they're online applications, involves a lot of listings of multiple items at once and selecting individual items occasionally. Where those individual items are selected, that's where you need third normal form. They're rare. So what is third normal form? I like to think of third normal form as a resolution of many-to-many relationships. In this situation we have a course and a student. A course at a university can have many students. A student can be enrolled in many courses. The result of this is that there's a many-to-many relationship between the course and the student, because the course can have many students and the student can have many courses. So how do we find an individual student per course? Well, Think about it. Would you ever really want to do that for an application? You might, sometimes. That's why I say third normal form is occasional. Third normal form is generally a many-to-many resolution entity, which is what we see here, the course student. All we're doing is we're taking the course ID and the student ID and joining them together into a new entity, which allows us to find that individual item. That's third normal form. You decide whether it's useful or not. Now for fourth and fifth normal forms. Fourth normal form, this is an example, and this is an example of fifth normal form. Fourth normal form. Fourth normal form. Technically, in published definitions of normalization, fourth normal form is described as being intended to separate multi-valued facts in single tables into multiple tables. Fifth normal form, on the other hand, is intended to divide related columns into separate tables based on those relationships. Make sense of that? I never tried to. That's why I say normalization is for academics. The simplest way that I see fourth normal form is that its intended use is to remove null capable fields from an object such that we don't create lots of rows in a table where a lot of the columns in each row are null. So what do? We take the null valued columns and we put them into a separate table. So what's actually happened here in this employees entity is that the skills and certifications, in this case these are probably going to be very large character data types, and we've taken the skills and certifications columns and removed them into separate tables. This is nice. However, it does create problems later on when you need to select data, because what happens is that, let's say we want to select all the information in this entity. So we're going to select employees and their skills and certifications and bring them up in a query. With these tables having had fourth normal form applied, we have to actually do a join on three tables. Not a problem if the data's a small amount. If we've got millions of rows, the performance of a query retrieving this data could be huge, could be a huge problem. That's where fourth normal form would fall down. Let's go to fifth normal form. In some ways I actually find fifth normal form a little easier to explain. In this object here, employee, we have product, manager, and employee. In theory, each of these items is related to each of the other items. So therefore, because you could end up with composite indexes across each combination, as in product, manager, employee, or just product, manager, employee, product, employee, manager, employee, etc., etc. The list goes on. It's a combination, basically. What we can do is we can create three separate entities, which relate three with each other in twos, for instance. So we've got employee manager, and we've got manager product, and employee product. That's fifth normal form. What I'd like to do now is to go back and present a brief summary of all the different normal forms. So what can we say about the different levels of normalization? How can we summarize? First normal form removes repetition by creating one-to-many relationships. Second normal form creates not one-to-many relationships, but many-to-one relationships in order to separate static and dynamic information. Third normal form is used to resolve many-to-many relationships into unique values, effectively creating many-to-many join resolution entities. Fourth normal form, as I understand it, is used to minimize on nulls. And fifth normal form is used to reduce the number of composite keys. That's normalization. What is denormalization? Denormalization is really normalization in reverse. However, I like to include a number of other things, namely data warehousing, which is effectively a database that's created for amongst other things, reporting purposes. Data warehouses are generally a denormalized form of a live, active, or online client-server database to allow for faster access to information. Part of the process of creating data warehouse data and tables from an active database is a partial process of denormalization. Data warehousing is much more extensive than just denormalization, though. I'd like to put another subject area into denormalization as well. It's not really denormalization and it's not really normalization, and that is the area of separating different usage data. What do I mean by separating different usage data? What I mean is, for instance, taking highly active and highly inactive or historical data and separating those two types of data into different parts, different tables, different databases, whatever you like. Separation. For instance, if you had an accounting system and you've been using that accounting system and building up data for the last 5 years, and you really only want to look at the current month, what would be the point of writing select statements to read everything over 5 years when you only want to look at your active monthly figures? If your database was small, it wouldn't be a problem. If you had a couple of hundred gigabytes, terabytes, it would make a huge difference to the speed of your queries. That's what denormalization is. It's really partially the opposite of normalization, but it also includes a few other more specialized areas. Why do we need denormalization? Why denormalize? Why take a complex, well broken down, divided up structure that lends to simplicity and effectively make it more complicated by taking data and sticking it back together again? The biggest problem with over-normalization is it causes performance problems. Normalization is really an academic thing. Denormalization is the commercial application of normalization. In other words, normalization is academic in that it goes way too far in breaking things down, and denormalization attempts to put things back together again. Denormalization will make your entities less complicated, and it will make your data more complicated, effectively, because you're going to have fewer entities, but you're going to have the data in one place rather than in multiple places. Normalization causes performance problems, so we denormalize to compensate for those performance problems. If you have fourth and fifth normal form, you have lots and lots of tables, you run a query against all those tables, you're doing effectively extremely complex multi-table joins. That is extremely slow, and it's also very difficult to tune SQL statements like that. A SQL statement with 15, 20, 30 tables in it is just impossible to make it run any faster without doing steps in between, which really what those steps are effectively are denormalization to some extent. Another reason to denormalize, which we partially already mentioned, is an over-complex table structure. In some ways, a table structure with lots and lots of tables is very well broken down, and as you know, in terms of the object methodology, breaking things down into smaller parts actually creates simplicity, believe it or not, but it does. In a relational table structure, breaking things down too far in terms of normalization can actually cause problems. Remember, relational is not object, they're two totally different things. Denormalization actually takes a very granular table structure and makes it less granular. In other words, it creates fewer tables by sticking data together to make your SQL statements less complicated and thus faster. Again, complicated multiple table joins. Why denormalize? Because they're very slow. They can be very slow, they can be impossible to tune. They're just very difficult to deal with. Back to separating different usage data in terms of separating active data from large quantities of historical data. Reporting against application tables. Really, what this is actually the same thing as data warehousing. Your live online or client-server applications on a day-to-day basis are changing data, they're inserting, updating, deleting. If you go and run reports against those same tables, the two different aspects or applications are competing with each other. Your reporting application and your live client-server online applications are competing with each other for resources, machine resources, database resources. They're looking at the same data. You could have locking issues. The reporting tends to coagulate information. It denormalizes to read the information. So it tends to look at a lot of stuff at once, particularly when it's looking at application table structures. can cause problems. Key indicators. What are key indicators? Key indicators in this situation are things that are indicative of an over-normalized database that may require denormalization to help speed up its performance. All I'm going to do at this stage is just mention what they are. One-to-one relationships. Generally fourth normal form, perhaps dividing tables up much too far, creating very large SQL statements on multiple table joins. Many-to-many join entities. Look for many-to-many join entities which have a name which is not meaningful. Over-normalized static data. Static data can be removed from transactional data sometimes a little bit too far. I like to think of normalized static data as second normal form. Tables with a very small number of columns, very few columns, quite often indicates a table which could have its columns in a parent table. It shouldn't really exist. Fourth normal form, denormalization. My key indicator here would be one-to-one joins. This is a one-to-one join, so is this. What I've done is I've denormalized one of the one-to-one joins, namely the listed entity, and then I've denormalized the address one-to-one join. Everything ends up in the customer table. Why would you want to do this? Because the SQL statement here would look at 3 tables, and in this case it would look at 1 table. Fourth normal form attempts to remove potentially nullable objects such as the customer address detail and the stock market ticker symbol from the customer object. In my mind, this is academic. It's not commercially practical. What actually happens is you remove these null objects from here. There's no need to do that because they're null. They don't take up any space. It creates a more complex table structure in fourth normal form, which is intelligent in terms of reducing complexity. Believe it or not, that does actually happen, but that is more sort of an object methodology rather than a relational methodology. There is no point in doing this. This is the much better form of the customer table. A SQL statement here would require a multiple table join on 3 tables. In this case, it would be against a single table. If you were to add all sorts of other information to a query, for instance, sales orders, purchase orders, sales invoices, purchase invoices, you could end up with huge joins which are very slow and impossible to tune. Meaningful third normal form. What do I mean by meaningful third normal form? Take this example. I have a database or a table structure which represents, for instance, pop concerts or pop acts doing many shows at many venues all over the country. They have supporting acts. Quite often, not always, but quite often. A supporting act is also an act. Therefore, the relationship between the act entity and the show entity is actually one-to-many or many-to-many. The many-to-many relationship between the act and the show entities can be resolved into a single entity called supporting act. It is meaningful. It has a name which makes sense. It says supporting act. Here's another many-to-many resolution join. I call this one meaningless because all we've done is we've taken the course entity and the student entity, placed them together and called it course student. We do not have a specific name for it that means something else other than course student. This is the type of many-to-many relationship that I look for, because quite often they're unnecessary. They're created because they exist, but they are not necessarily used by the application. Think about it. Let's say you have an application that will list courses, so you'll pick a course from that list and you'll get a list of students. So you could click a single student and get the information for that student on that particular course. The chances are you don't need to go to the database to select that information. It's already in memory in the application. The same would apply the other way around, where you would look through a list of students and find all the courses that they do, and then you could select an individual course for that particular student. If there's any information that's applicable to the course-student combination, it is probably already in memory. The only situation where an entity like this is needed is where there are extensive fields that are applicable to the course-student combination. It's unlikely. There is a many-to-many relationship between these two entities, but it doesn't necessarily have to exist. That's my point. Don't create many-to-many join resolution entities unless they're actually used. Second normal form, denormalization. This is the fourth normal form example we used earlier. This is the same example, except we have the separation of a static item of data from the listed entity. What I've actually done is I've said that our customers, some of them will have ticker symbols, and they will be listed on a certain stock exchange. The point is this: how many records will be in this table? How many stock exchanges exist? Assuming we're looking at Fortune 500 customers, the chances are they're only going to be NYSE and perhaps the NASDAQ. There's no point in this entity existing because they'll have one or two records. Watch for that. Static entities with a very small number of records. That can cause problems because to read from the customer information to find his address, his listed object, plus the exchange information, you're reading from 4 tables. Practically all that information should be in a single table.